Hello, everyone. Welcome to this third session of the second part of Beyond Bohm, David Bohm and Philosophy. I'm James C. Barbieri, Associate Program Director here at the Prize Center, and I will be your host for today. As a host, I'm here to help you throughout the call. So any issues, technical or not, feel free to let me know in the chat. Before we begin, let me just very briefly go through a few guidelines for this call. Firstly, if you can please mute your microphone to ensure good quality audio, but at the same time, we do encourage you all to turn on your cameras. The chat is open throughout the call, so feel free to use it to share your thoughts, ideas, or material inspired by this call. And of course, you can also use it for Q&A to ask your questions. We also have closed captions now, which you should be able to see. If you find them distracting, you can select the closed caption button, press hide subtitles, and it should come off. Finally, the session is recorded for archival purposes and for you all. The recording should be available in a few days, and you'll get a link for this once ready. So today we are honored to be joined by Basil Hiley, who will be interviewed by Petteri Limnell. Petteri teaches 2 ongoing courses at the Pori Municipality Center and has worked as a consultant, teacher, tutor, and in-house philosopher at the Pori Art Museum. He also works for the Critical College of Finland and runs Satakunta Critical College in Pori. He has also been president of the Pori Philosophical Society for 11 years, and his main interests in philosophy relate to 3 of Popper's emergent worlds. We also have Basil, who is, I'm sure you all know him, but he's a British quantum physicist and professor emeritus of the University of London. He received the Majorana Prize Best Person in Physics in 2012. He was a longtime co-worker of David Bohm. He is mostly known for his work with Bohm on the implicate order and for his work on algebraic descriptions of quantum physics in terms of underlying symplectic and orthogonal Clifford algebras. Hiley co-authored the book Undivided Universe with David Bohm, which is considered the main reference point for Bohm's interpretation of quantum theory. Today, Basil and Petteri will be discussing the role of philosophy in Bohm and Hiley's research in physics. And with that, I'll hand it over to both of you. Welcome.
Thank you very much.
Yes, thank you very much. Hello, everybody. Hope you're having a good day. Petteri, you're in charge.
Okay, if I'm in charge, is there something in the beginning you would like to say?
I would like, I think when we were talking with Paavo a couple of weeks ago, I did get some interest when I said that I've actually pushed the Bohm theory, what we wrote in the Undivided Universe, a lot closer. We include now relativity in a very clear way. And I've been developing that, and I'd just like to show how it has developed at some stage. Okay, is that all right?
Yes, that is all right.
Okay. Now, what prompted me to move in this direction? I think we need a bit of background to it. I came across a paper by Bryce DeWitt. Now, Bryce DeWitt was a cosmologist and a very, very excellent mathematician. And the paper talks about the quantum potential quite freely. And the paper, where was it published? It was published in the Physical Review. And what year was it published? 1952, which was the year that David Bohm published his paper in the same journal. The difference between the two was David's work was in issue 2 and DeWitt's work was in issue 4. And do you know, the whole time I worked with David was too long to remember, there was no mention of this paper at all. And in the paper, DeWitt actually says that the quantum potential is necessary to complete the quantum mechanics at that level. And the principle he was using was the general principle of covariance, which is the principle that Einstein was using, the general principle of equivalence. What that means is, in order to get an expression which is correct for all reference systems, you have to add the quantum potential to the classical Hamiltonian. And that comes in as order h bar squared. What I have never understood is why I had to get till I'm almost off the planet to realize this paper had been written. Nobody who discussed, in my ESOP, who discussed Bohmian mechanics, the Bohm theory, blah, 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 nobody mentioned this paper at all. And I find that extraordinary. The interesting thing is that not long after I found that paper, Michael Berry also published a paper and showed how the quantum potential arises in ordinary classical wave optics. He actually calls it the quantum potential and actually shows that it's related to the curvature of space. Now, if you remember, general relativity is all about curvature of space. So it's interesting. Why did DeWitt suddenly stop? And I'm afraid I have not got to the bottom of it. I had a report, and I'd be very interested in any information that anybody can find about why DeWitt dropped that particular approach and went on to his many worlds or his many worlds interpretation, which was quite extraordinary for me. Anyway, so that's the background. And as I was developing, I'm trying to understand what they had done, what Berry had done, what DeWitt had done, it suddenly opened up a whole new vista for me for the Bohm theory. It was quite extraordinary. Now, I can't tell you the whole story, but let me just say, I've got a little summary, because most people, if you talk to, they'll say, Bohm theory, I don't like it. And if you ever say, why? You never get a straight answer. Heisenberg actually said, oh, it's the quantum potential is ad hoc. And yet it comes straight out of the Schrodinger equation if you write it in its, if you write the wave function in its polar form, RE to the IS. So, why did these people not like that? And I think the main reason is that they were absolutely obsessed with the Heisenberg uncertainty principle. You cannot do physics in phase space. In other words, you cannot talk simultaneously about P and X. So you cannot talk about momentum and you cannot talk about position. So what one finds is that these people had actually moved to the algebra of P and X. And that's the algebra that satisfies the non-commutativity. And that's the, so what they've done is they ignore the algebra as a description process, focus on the eigenvalues. The eigenvalues cannot be given simultaneous values, and therefore they say there is an uncertainty principle and therefore you mustn't violate it. Now, first of all, there is an uncertainty principle and you can't violate it. It's to do with the eigenvalues, but the point is the operators, the algebraic approach, which I keep trying to emphasize, doesn't depend upon the eigenvalues. The eigenvalues are folded up in the algebra, just as David Bohm talks about the implicate order unfolding into the explicate order. So what the eigenvalues are telling you about explicate order. But what they're not saying is when you make the explicate order in the position representation, it becomes implicate in the momentum representation, but in such a way that if you now explicate the momentum representation, so whatever you've done to the position representation, the momentum representation still agrees with the overall algebra. So the overall algebra is absolutely vital in this story. Okay, so that's point number one. Now, it doesn't mean when I'm talking, I don't say the Heisenberg uncertainty principle is not true. That's not what I'm saying. I'm saying it is true if you measure the position or you measure the momentum. But does measuring them say anything about what they actually are when you don't measure them? So you've got this ambiguity. Let's keep it open. You see, I think this is a relic of the positivism that says you must only talk about things that can be observed. We've moved a long, long way from that. And now there's a tremendous development in what is known as non-commutative algebra or non-commutative geometry, which gives you a geometry which is very different from the classical geometry of Euclid, Riemannian, and Einstein's curve geometry. I'm not going to take you through that and show you that because it's a long job. But what I want to do is just to show you something that Clifford did, because you often see me associated with Clifford algebras. Why the hell is he obsessed with Clifford? Clifford died, I think, in 1890 something, but he wrote a very interesting book, and the title, I knew this would happen, it eludes me for the minute. It's on the net. I think no, I can't remember the title, forgive me. But what it does is it develops this algebra, and when I was reading it, I found that it had all the equations that we needed in quantum mechanics already in it. And he knew nothing about quantum mechanics because in 1850s, 60s, quantum mechanics was hardly even mentioned. Okay, so let me just show you, because I think it brings in very nicely this idea of wholeness in a new way, which I haven't talked about before, and it may help people. And then we'll get on to the philosophy, because I haven't worked out the philosophy yet, but let's just have a look at some pictures to see what is going on. Can everybody see that screen?
Yes.
Yep. Okay, so what you have here is that there is a hierarchy of Clifford algebras. And I say Clifford, there you are, 1878 is the book I'm talking about. He was talking about classical physics, but he invented a process-based algebra for classical physics. What that means is when you're doing mathematics, you don't take two abstract numbers and multiply them together. You take 2 and you double it to get 4, or you treble it to get 6. It's the trebling that is the activity that is going on. And he was looking at mathematics purely in those terms. Now, what about this? It's not, I know the weather's very hot in the UK, it's not ice cream cone days, but if you look at this, this is the summary of Clifford's algebra. You start down here and you end up down here. I'll tell you what these things are in a minute. But this is essentially where the Schrödinger equation comes in, because these are isomorphic to the complex numbers. Then you have a next level are the quaternions. Now in the UK, quaternions have a funny history. They were not liked, but now if you're someone who's interested in robotics, you use quaternions all the time. Why? Because you're dealing with translations and rotations. Yeah. Think of a robot's arm. He's moving out to get something, picks something up, turns it, moves it in, does the screw, and you're building a car. Well, the principle is that. So that's that used. And then we discovered spin in quantum mechanics. And that appears at this level, 3-0, with the Pauli equation. And these are the Pauli spinners that people who know about physics will see left, right, and center in their textbooks. Then we move up one and we get to Dirac. And Dirac is in here, the Dirac equation. It's all in this algebra. And here are the gamma matrices for those who know. For those who don't know, it's the ones that are used daily by relativistic physicists. Then we've got an exotic de Sitter. And then we come up to the conformal. Every time we're increasing y1. The conformal, that's where Penrose lives. These are Penrose's twisters, the cycles of time, etc., lives up here. And these are just the generating elements which generate my algebra. And they all stem from a very simple formula that if you want to go up the ladder, this actually goes up two steps at a time, but I don't want to go into the technicalities of that. And that is the CP plus 1, Q plus 1. In other words, forget about the order. This is 3, 2 goes to 3. And you want to add in another 1, which is that one there. You do it by taking the lower order and just adding this extra term in. Now, what does this mean? Well, this actually leads us to the geometry of wholeness. And you'll notice I've got something here called universal time. So this is Newtonian time. And what we do is we start at the Pauli level where we've got 2 variables. Forget about the minus signs, because whenever you describe a circle, it's x squared plus y squared. So it's just got a minus sign for convenience. And you can split that into real and imaginary parts. And this, thinking about Clifford saying multiplying by I means rotating through 90 degrees. That's all it means. Nothing spectacular, just rotate it through 90 degrees. And this one says rotate it through 90 degrees in the opposite direction. Okay, so we've got our robot arm moving forward, rotate it this way or that way, and off you go. So you've got a way of describing the robot arm. Now we come to physics. Now we want to use this step-up function. And what you find is you replace Flatland. I don't know how many people have read that amusing book, Flatland, which is a 2-dimensional geometry, which Edwin Abbott tells some lovely stories about. If you want to get out of Flatland, you've got to get out and do it properly so the quantum mechanics is preserved. You do it by this. See, 1, 1, you add the 1 in there, 3, you add the 1 in there, that's 3. Simple as that. So special relativity comes by stepping up the tower. So you introduce 2 new variables. Notice here you only got x and y. Here you do t plus z and t minus z. Why do you do that? Well, these happen to be what Dirac called the light cone coordinates. there's something to do with light, the description of the light cone, how the light cones stack together. And if you split them this way, you see you can split your quadratic form into two linear forms. And that's what Clifford algebra, simple as that, what Clifford algebra, what Clifford realized, that you always split your quadratic form. This tells you how far you go. This is a distance variable. It tells you about the energy. And remember, Dirac actually linearized the quadratic energy because he was getting negative energies and he wanted to get rid of them. You then factorize it like this, and what have you got? Then you can stack, this is the light cone coordinate going in the posit. So you have a point here, Z plus. So this is a new t, which is different from universal time. Universal time is tau, the proper time. And here is the minus t. So you're coming in from the past into the future. So this process tells you how to come from the past light cone into the future light cone. So it's telling you the activity of moving forward. And then if you do what Penrose does and writes this array as a 2 by 2 matrix, then you get his incidence relation, he calls it. And these are just the Pauli spin matrices. And the quaternion is just something very simple. It's got real numbers A, B, C, and D, but now we've got I squared equals -1, J squared equals -1, K squared equals -1. So what you've done is you've now introduced 3 turns through 90 degrees. One in the XY plane, one in the XZ plane, and the other in the other plane. So you're just stacking 3-dimensional objects together, keeping the rotations clear. And then just one more. Now, so what, oh, wait a minute, before we go there, let me go back again. So what this is saying is that this is the space-time we live in. This is our T, is in here, not that T. And in this space-time, our T moves coherently as a whole with X, Y, and Z into the future moment. So we're actually moving as a whole. The whole structure is moving. And then when you go to Penrose, you then do exactly the same thing, only now you introduce a new time. Yeah, we got lots of times around here, mate, plenty for philosophy to worry about, and a new parameter. And you deal with this in a way which I can't go into here. But our time is still here, and it's now moving through universal time. And the Dirac spinners and the Penrose twisters can be related in this particular way. It's 2. I've got 1 and 2, 1, 1, 2, 2. This is one light cone. This is the other light cone structure. And what Penrose was very clever in doing was showing us how we relate the distance between light cones in our geometry. And this was the work that David and I published in way back, not as clearly as I've done here, way back in 1984. And that paper was ignored, possibly because it was rather difficult journal to do. Why did we publish it in the Revista Brasileira de Física? Because the main idea comes from when David Bohm was in exile in Sao Paulo. He met a guy called Mario Schoenberg, and Mario Schoenberg had these ideas of a quantum geometry. So this is the essential new features of quantum geometry. Well, it's not that new because we had it in 1984, but I can now talk about it very freely as something new. And it's moving, we're all moving on a space with this space-like surface through space and time. Okay, so the point being now, and all of the Bohm's work comes out of this tower. We've got quantum potential for the Pauli, we've got quantum potential for the Dirac, and I didn't bother getting the quantum potential out for the conformal. But all the quantum potential emerges from this, so we have quantum potentials sitting inside each other, a very rich structure. So this covers all of physics with the Bohm theory. Thank you for being patient with that, Petteri, but I just wanted to show that it's not the Mickey Mouse model, as Harold Atmansparker calls the original Bohm theory. There is a structure, hierarchy of process in there, which you philosophers, Petteri, have got to sort out for us.
The process philosophy and the kind of a process physics that you do, it is physics of space and time, right?
Yeah.
Yeah. And so some people say that, okay, that a special relativity is a theory that understands time the best possible way.
It only partially understands time.
I'm sorry.
It only partially understands time in my theory.
All right, because some people say that, you know, special relativity talks about kind of a block space where past, present, and future are equally real. Is this correct?
No, this is not what I'm saying. This is not what we were saying. We were saying that the block, the space-time, space-like surface, is that all right? That's where the X's and the T's and Y's are. That all moves together. We're moving, we're sitting on here, we're moving. It's not a block universe. We can do creative things on it.
So there seems to be a general future, genuine future also.
Yeah, a genuine unknown future.
Mm-hmm. So it's not already there.
No.
Block space. Okay.
No.
How about the past? Is past real in this model of yours?
It's past real, but it leaves a trace in what we are going to do tomorrow.
Mm-hmm.
As you well know, if I've got a bad eye which was operated on yesterday, there are things tomorrow that I can't do. Mm-hmm. Whereas if I hadn't got a bad eye, I would have done something else. So it's not a block, it's open, and it depends upon the history, the past history.
Okay, but how about relativity? If we're talking about block space, and when they say that the past is equally real as the present and future, in theory, if you could possibly travel back in time, could
but Petteri, don't forget, I'm saying everything is about activity. I'm not saying everything is static. I'm Heraclitan to a T.
Yes, I understand that. Yeah, yeah. But how do you cope that? How do you cope all that with relativity physics?
Because the formulae fortunately captures all that to make sure you don't go wrong. Because you've got the quadratic form telling you what the conservation laws are, and then you've got how the individual must behave in order to obey those conservation laws.
Okay. How does general relativity fit into?
Now, please, slowly.
Oh, okay.
I haven't got there yet.
Right. Okay.
Okay, but I can say something about it later because I don't want to confuse people by bringing in some more structure. So if you can sort of confine your questions to this. I don't have the answer to general relativity, otherwise I wouldn't be sitting here, I'd be in Sweden.
Right. can understand that, yes. But now, if we're talking about the time, we can say that time is a pretty tricky concept in both in philosophy, if you read the Magna Carta or the classics, but it's also a tricky concept in physics, both in quantum and relativity. And they say that the special relativity understands time the best possible way. You don't necessarily,
the best possible way at the moment, but I'm now suggesting a new way.
Okay, I'm satisfied with that.
Let's be brave. Let's explore.
Exactly. Can you say something about time in quantum physics? Because it's been said that I remember we once talked about this, and you mentioned that we have to talk about something like quantum clocks, but I'm not quite sure whether I understand what this is. And then some critics says that we don't do anything with these quantum clocks because they don't show time. So
yeah,
what is your...
No, it to me, it once again, it's the process. Now, how can I answer this one? It's really the process, you see, because while let me go back to remember you were talking about these eigenvalues. So you're looking for an eigenvalue of time, okay? Because that's what we say physics corresponds to the eigenvalues of the operators. Of course, you get into a bit of a mess because people say there's no operator in time, no time operator, etc., etc. But I'm saying, forget that for the moment. If you follow this algebraic process, what you find is that everything really comes from 2-point functions. We've been trying to do everything at a point. But if you look at the light cones I've just shown you, you can sort of see there's a forward light cone and a past light cone. So there's a separation between these two concepts. And how do they develop? Now, normally, when you're doing, I'm going off topic just a minute. If you're doing differentiation, you assume that the differentiation occurs at the point. Yeah. You say delta x1 minus x2 over t1 minus t2 is the velocity at that point. But the question I ask, which point? X1 or X2? And it makes a difference because X2 will be in the past and X1 will be in the future in this way of looking at things. So you've got to see how that develops. And now what you've got to do is you've got to look at time in the same way. You have moments in which you have T1 and T2, because I'm dividing that equation for the velocity is T2 minus T1, or whichever way around I put it. Yep, the difference. But then you need a mean time. So you've now already got 2 times. A moment where where time is not defined. It's just things are happening. And then time becomes defined, but there is a mean time which can map you through this process. Does that help?
Is it a different kind of time? I mean, when you're talking about these planes where we have the 3 dimensions plus time, and if that plane moves, does that move in another dimension?
No, we don't. We don't have
time dimension.
Petteri, we don't have time plus 3 dimensions. We have 2 dimensions, time plus another dimension. And when we go up, we have time plus another dimension. We're increasing the number of dimensions as we go up the tower of Clifford algebras. I'm sorry, it's a difficult concept, but that is what's coming out of what I'm doing.
All right.
And that's what we've got to get our heads round.
Okay.
In philosophical terms.
Yeah, there are some physicists who says that there's no problem of time in physics at all. How would you answer to these?
Well, I feel very happy for them. They don't have to stay awake at night or having a cup of coffee answering questions from people like you and members of the audience.
Right.
It's not, there is a parameter T, but is that, you see, David Bohm actually had an idea that the time in Schrodinger's equation was actually not the time that we measure by a clock, but by the implication parameter T. It was to do with the folding and unfolding, the time of folding and unfolding.
Right. Okay.
And it takes a finite time. So you have this uncertainty, just as you have the uncertainty in position and momentum simultaneously, you're going to have an uncertainty in time and energy simultaneously. And you have to deal with that.
Okay. But in general, it seems to be that the time in physics is a little bit different than the time in human experience when we have past.
Yes, because they're using the time as just a parameter T, and they think that is the real McCoy. Okay. But it's just a parameter.
Yeah.
Okay.
Yeah, all right. I would like to go, next I would like to, let's talk about physics and the ideas you have in your theory and so, but I would, a couple of weeks ago, we were talking about creativity and freedom, and we touched these topics a little bit, and I have a few questions here I would like to go on with, and I hope that you find this interesting, because this is a tricky topic also. So, in your opinion, is there real creativity in nature? In a sense that how much freedom there is in nature, and therefore how much creativity there really could be in nature. I mean, in an old-fashioned sense, old-fashioned philosophy, they say that there are no new beginnings. And if so, what would you consider to be such new beginnings? And also there is this question, so there is something in physics called degrees of freedom. What are these, and might these have something to do with natural freedom and creativity?
Yeah, the problem is that physics tries to say that there is no ambiguity in nature. Right?
Right.
But what I am finding is that there is an ambiguity in nature. There is an ambiguity when time is not specified. For instance, if I know exactly what the energy is, the time is not specified. So within that process, there is freedom for creativity.
I see, okay.
Yeah, because the process can develop within that ambiguity. If everything was as in classical physics, we would never create anything, because everything is geared into the processes that are going on at a point. It's not allowing the possibility of, when you come to the next moment, of going through different paths. It's very much like when I was plotting the quantum potential, I was talking to, oh my God, I'm sorry, I get so, names elude me. Brian Goodwin, they come slowly. Brian Goodwin, who was a biologist. And he introduced me to the idea of Waddington. where you have the development of the neural network through the creodes developed in a field of potentials. But at every point there is a junction, and you can go off in different directions. I look at creativity as being occurring there in that model. But in my model, it's better because we have the ambiguity in time. So we can't say that is going on at that particular time. If we try to keep the time control, we destroy the process.
So
Now,
we really don't need to worry about the old classical concepts like determinism and indeterminism.
No, because if you've got ambiguity, what does determinism mean?
Right.
It doesn't. It goes out of the window.
Okay.
The old determinism was very much based on the classical physics. Yeah.
Yeah.
But now what quantum mechanics is suggesting, I'm not sure whether this is correct or not, but this is what it's suggesting to me, is that there is a basic ambiguity. Now, it's not so ambiguous that we can't make sense of anything. This is the cunning thing. It's ambiguous within a short scale length. For example, like h bar squared or something. So that brings in the degree of ambiguity. And that's very small. I mean, it's you know, the quantum algebra is almost commutative because it's just that little p comma x is equal to IH bar that gives you the uncertainty principle. But if you take it further mathematically, everything drops out.
But we still do have the causality in physics, and it seems to be that it has still.
We've got to be careful. What do we mean by causality?
I know that's a very good question.
Yeah. Because to me now, if position and momentum are essentially ambiguous, causality becomes ambiguous. There is a flowing movement. So there is a cause in that sense. So Petteri, what does Heraclitus say about causality? Have you ever looked at that?
Well, I'm not sure what he said about causality per se, but of course, if we think about it within the context of this ongoing process,
yeah,
seems to be ambiguity right there.
Yeah, but there is yeah, sorry, I please forgive me if I interrupt. I'm
no, it's all right.
I'm a terrible debater.
Yeah, let's go on.
Yeah, if you've got ambiguity, it doesn't mean to say there is no cause, because there is this flowing movement, which, if you like, is the cause, but there's no precise cause. Why did he take the left hand instead of the right hand? There's no causality in that sense. He could have either taken left or taken right. And there's nothing to determine why. So that's where, if you like, the free will begins to come in. Wow, that's a leap. Yeah.
Yeah, if you want to go there, please.
No, I'm just saying that's where it could come in. And then, of course, there's always the Schopenhauer idea of, are you free to will? I mean,
if you're really free, can you be able to choose freely?
Yeah. Oh, please remember that within this ambiguity, you have to satisfy the algebra of quantum mechanics. That's the governing, for me at the moment, that's the governing process. the algebra must not be violated. So it's in that sense that you can have creativity and yet put boundaries. And if the creativity occurs in the eigenvalues, if you want to say that's where the process is actually discussed, the eigenvalues get spread all over the place. I mean, it's quite phenomenal. If you're in the X representation, like, can I take a point up actually about randomness? Quantum mechanics is not random. There's no randomness in quantum mechanics. Oh, better be careful. That's asking for an elephant trap, isn't it? There is limited randomness in quantum mechanics. Because whatever you say about the position representation, you've got to make, so that's all the eigenvalues of the positions. You've got to make sure that what is going on in the complementary algebra. Remember, Bohr always talked about those regions of that algebra which everything commuted with everything else. And then there was the rest. In other words, everything that commuted with X is in the configuration space. Everything that is in commutes with P is in another space, which is not accessible when we're playing around with configuration space. What's going on there? And what you find is that actually to go from one to the other, each point and configuration space is exploded into all points in momentum space and vice versa. So these transformations are not just, oh, simple. There is a process going on when you do that kind of thing. And you've got to make sure it's all satisfied. I'm not sure that I've got that point over. You see, because you've got everything, all the eigenvalues are well defined in this algebra. That's the commutant, but the rest of the algebra, they're not defined. And P is in this algebra, P is here, but it's not defined in the P representation. The eigenvalues are somewhere scrambled up all over the place. And that's what I think we haven't really got hold of. You see, have I got across the point? Go on, say no.
I'm not sure whether I understand everything you say, but let me continue asking this more general question. What do you think about reductionism? I mean, everybody says that it's so victorious.
No.
Believe that you don't believe that.
No, because I can't have reductionism, because as I get closer and closer to measure my position, my momentum gets further and further apart. So how's that working? If you forget about this, see, and any non-commuting, let me try and make it clear. Any non-commuting algebra has elements that commute with each other and elements that commute with each other in a different setup. So when you're working with this subalgebra, the subalgebra that you've left out, you've got no control whatsoever over, except through the total algebra. Petteri, do you see what I'm trying to draw? If everything was commutative, then everything is well defined. But as soon as you have non-commutativity of any kind, you split your algebra into different representations, which can be diagonalized simultaneously. But if you diagonalize them in one representation, you cannot do it in the other representation. So while you're working in this representation, say, oh, X is here, now it's moved to there. What's happened to the other representation? You take no notice of it. But the overall algebra is telling you what's happening to it. It's moving in a very complicated way. It's not like classical geometry. That's the problem. And I don't think we've still got our heads around the fact that we have to deal with a non-commutative geometry. It's something which I know I speak for myself, but I sort of, oh my God, every time you try to think about it. But now I'm beginning to get a handle on it, but it's been a lot of tough work. And there's been a lot of work done actually with the mathematicians on this. And they really have moved it on quite considerably.
Okay, I continue to ask this, that people usually say that physics is about structures and basically nothing but structures. So what new can we find in physics possibly than structures? And what kind of structures and if there are new entities, what kind of entities those would be?
My
entities really matter.
Yeah, my structure, I've still got structures there.
Mm-hmm.
I still got structures. I've got, you see, normally in ordinary geometry, we have vectors, we have triangles, we have squares, etc. And normally we say vectors always go into vectors. Triangles always go into triangles. Squares always go into squares. In other words, they keep their identity when we look at it in different ways. Yep. But get that in quantum theory. Sometimes a little bit of a vector gets turned into a triangle. Sometimes a triangle gets turned into a little bit of vector. Get your head around that one. Because that is what is the key to this Clifford algebra stuff. That you don't keep them separate. Now, Gibbs saw that. Willard Gibbs, yeah, thermodynamics man. He saw that at the turn of the century and said, we won't have anything to do with Clifford. Did you realize that? He wanted vectors to go to vectors, bivectors, that's triangles to go to triangles, squares to go to squares. That's all we have in physics. Okay. Then there was a young man called Paul Dirac who came up. And remember, he had this E squared minus P squared equals M squared. That's the conservation of energy. And that, if you take the square root, you've got E is going to be plus or minus. And at that stage, he had no idea what to do with negative energy and positive energy. He didn't want negative energy anywhere in the building. So what he did was he linearized that quadratic form. And of course, the linearization gave you the actual structure that I illustrated at the beginning of the talk, or the beginning of the interview. So the structure's still there, but it's what we do with the structure and how they transform into each other. You see, you cannot use classical causal arguments of a bit of vector going into a bit of a triangle. You're probably looking at me saying, what the flaming hell is he talking about?
Well, let me. Yeah. Do you want to continue with this or?
Yeah, I just say that's what the algebra does for you.
Okay.
It has this flex. It's a process, you see.
Yes. Let's talk about this process and movement a little bit later. But at this point, I would like to ask you that we talked about a little bit of reductionism, and usually we're talking about mechanisms, and when we are trying to explain something, we are trying to find the mechanics, and then we say that, okay, now we can explain something. But you have been talking about organic worldview, also in the context of quantum physics. Now, what kind of thinking there is behind these thoughts?
It's really chemistry.
Okay.
Remember, there are two types of chemistry. inorganic and organic.
Okay.
And what is the main driving source of organic chemistry? It's quantum mechanics. They
All
can't
right.
do organic theories without quantum mechanics.
Mhm.
And that's the snub answer of it, as it were. Because you might say, oh, well, I can put balls and spokes and stuff together. It doesn't work. Actually, I wonder if I could, can I tell a little story about something which, when I was looking at this, about the translations and the rotations,
All right.
quite staggering. And you know what a garden hose is? Rubber hose which lets water in so you can water the garden.
Mhm.
Form it in a loop, put it in the tap there, garden there, and just have a look at the loop. And then start the loop oscillating, right? Swinging. And then get someone to turn the water on. And what do you find? It's no longer swinging. It actually gets turned. So the flowing water actually causes a rotation in that case. That's your gas meter, by the way. And then in quantum mechanics, if you look at the spectra from polyatomic molecules, you have a rotational spectrum and you have a vibrational spectrum. Those are the spectral lines. If the molecule is not rotating, the spectral lines are not of a harmonic oscillator. Sorry, are of a harmonic oscillator, I beg your pardon. If you start the atom rotating, you get this twisting effect, which you can actually see as a change in the energy levels. So there's something remarkable going on in this quantum mechanics. It's not now something completely different. It exploits the mechanical stuff to produce some rather interesting effects. Absolutely amazing. Anyway, I thought that might help, but it probably doesn't.
Well, this, let me see, I have to click here. Okay. When you're talking about wholeness and organic worldview, you seem to think that there is something very organic in this whole.
Yeah.
The whole is working like a big organism or something like that. Isn't that what you?
Yes, that's what I'm saying. Yeah.
That's what I'm saying. Okay. Now let me go back a little bit.
Oh, by the way, just first of all, we're supposed to be talking about Bohm philosophy as well. And Bohm agrees with me on this point. He calls it that quantum mechanics should be called quantum organics, I think it was.
Right.
We couldn't find a nice name. It always sounded ugly.
Okay.
And I think he published a paper in which he actually built up on this theme.
Let's get back to this, but before we continue, I would like to read a few lines here, because we're also talking about the role of philosophy in physics. Now, I have a paper here written by Carlo Rovelli, published in Scientific American back in 2018. This paper it's entitled Philosophy Needs Physics, Physics Needs Philosophy, Philosophy Needs Physics. He writes like this: contrary to claims about the irrelevance of philosophy for science, philosophy has always had and still has far more influence on physics than commonly assumed. Certain current anti-philosophical ideology has had damaging effects on the fertility of science. The recent momentous steps taken by experimental physics are all rebuttals of today's freely speculative attitude in theoretical physics. Empirical results such as the detection of Higgs particle and gravitational waves and the failure to detect supersymmetry where many expected it question the validity of philosophical assumptions common among theoretical physics, inviting us to engage in a clearer philosophical reflection on scientific method. And Against Philosophy is the title of a chapter of a book by one of the great physicists of the last generation, namely Steven Weinberg. Weinberg argues eloquently that philosophy is more damaging than helpful for physics. It is often a straitjacket that physicists have to free themselves from. Stephen Hawking famously wrote that philosophy is dead because the bigger questions that used to be discussed by philosophers are now in the hands of physicists. Neil deGrasse Tyson publicly stated that we learn about the expanding universe, we learn about quantum physics, each of which falls so far out of what you can deduce from your armchair that the whole community of philosophers was rendered essentially obsolete. So obviously, Rovelli disagrees. He says that philosophy has always played an essential role in the development of science, physics, and physics in particular, and is likely to continue to do so. Sorry, this was
Oh, okay, interesting question.
Took some time, but there seems to be some hostility among the physicists concerning philosophy. But then we do have physicists, for example, who thinks like Rovelli, Bohm, yourself, who seems to think that philosophical thought has some very interesting to tell us.
I think I think we have to say, what do you mean by philosophy?
Right. Okay, what do you think about it?
Because if you're saying Kant said so and so, and therefore that must be true,
right,
that is not the philosophy that I would be talking about.
Right.
I would rather say, why did Kant say that? Because
exactly.
that opens up certain pre-assumptions.
Yes.
And for those pre-assumptions are very useful in freeing us from them, because we don't know what those hidden assumptions are. We will never be free from them. And I don't think there is. David used to be very angry with people. He used to call it who let silent metaphysics dominate their thinking. You definitely, I'm gonna be sound assertive here. As far as I can see, you need philosophy, because how do you know when you're doing your calculations, it's not garbage in and garbage out? What do you feed into your calculations? You know, you're not given, you're fed in Schrodinger's equation, but then what alarms me is that nobody has ever asked, or they have actually, where does Schrodinger's equation come from? Okay, it's in Feynman's lecture notes 3, I think it is. And I think there he says it comes out of Schrodinger's head. Well, that is not a very helpful remark to make.
Right.
In other words, you know, what is it? Can we probe it deeper? Can we question how it arises and so on? There are a lot of people who come up with, oh, of course I know Schrodinger's equation, blah, 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 blah. But then when I show the relation between classical Poisson brackets and commutator brackets and the deformation quantum mechanics, they then begin to shut up. In other words, it's so easy just to say, I want a peaceful life. I'm sorry to say that. I've seen it God, I'm in my 80s. I've seen it happen time and time again. Young PhD students sat upon asking this type of question. It's not healthy for science. But I know why they're worried about it, because they think it's going to mislead you. So they don't think we have the intelligence to read the philosophy, to read the experimental results, to read what the theory says about the experimental results, and try to pull them all together and get something coherent from that total structure. And in that sense, I think Carlo is dead right, that we do need this philosophical background. When I was worrying about the pre-space ideas that
Let's talk about that a little bit also, yes.
Yeah, got me going on this, it was really, remember, I think it was probably Pava who said, but please, Basil, Kant says it's a priori given. What the hell does a priori given mean? And then I began to read Schelling, who begin to explain much more carefully this whole notion of process, and then into Fichte.
Yeah.
Which opened. And did you know that Hermann Weyl actually was influenced by Fichte?
Yeah, I think you told me about this. Yeah.
Okay, I told you about that. Okay. Yeah, well, you have privileged information. No, he's written a couple of papers in which he feels Fichte actually helped him. And Weyl has made a tremendous contribution to relativity and quantum mechanics. He's in the popular press don't praise him because it's too difficult for them to understand what he's saying. But if you talk to the real hard physicists, they say, yes, I think even Einstein said, that man knows what he's talking about.
And Niels Bohr was influenced by Søren Kierkegaard, Einstein, yes. Immanuel Kant, David Hume. I remember one letter from Einstein where he wrote that if he had never read David Hume, these lines and these lines, he would have never able to realize this and this. So yeah. He basically his debts to the philosophers. So back in the early days, physicists seemed to knew.
Yeah, and I think we
philosophy and value it. But now it seems to be a little bit different.
Well, because now we've got lots of tools in the tool bag, and we can play tricks with the tool bag, and not mathematical tool bag I'm talking about.
Right. Yes, yes.
And we don't, and we can say, oh well, we don't really need to know that. But in fact, we don't. We have to understand the tools. Where have they come from?
You have to be able to ask right questions, come up with the hopefully right premises, and also that. So
that's right. Yeah.
Thinking there.
Yeah. So we might, you know, the whole point of Clifford was to say, how do we know that when we go to the very small, what we see at our ordinary level continues down to the very small? Take a piece of paper. It looks smooth and you can draw pictures of the geometry on it. But when you examine it under a microscope, it's made of fibers. It's not smooth at all. So that's what he was very much into. How do we discuss the very small? It's a fascinating, I wish I could remember the name of it, something like the exact sciences and mathematics, or the mathematics of exact sciences. It's on the internet, for goodness sake, read it. Everybody, if people are interested, read it. It's very, very illuminating.
What do you think about thought experiments? Philosophers usually do thought experiments. Just like, for example, that if you want to know that what there really is in the world, you get rid of consciousness, mind, all the sentient agents, angels, whatever, and then you ask that what's left. Einstein was also a pretty good and is well known of his thought experiments. What do you think?
No, I agree. Well, thought experiments, I do a lot of thought experiments on the mathematics. In other words, when I'm pulling the mathematics to pieces, what would happen if I did this? What would happen if I did that? So that is equivalent, I think, to a thought experiment. You know, and then we can say, all right, look, I'm getting this. Is it working in the laboratory? So that's another way of doing a thought experiment.
Right. Okay.
So yes, I agree with that.
Yeah. All right. Last time when we talked 2 weeks ago, you already mentioned about, you were talking about movement and process. Seems to be two very important concepts in your work. So let me ask first this, that where did you get this idea or concept of process? How did it came to you? Is it from Hegel or? No,
I think really the first interaction with David Bohm really triggered me off. And he had a paper in '62, which I think was called Structure Process.
Right.
So already we've got 2 words there, which was new to me coming in from solid state physics. Well, structure was not new, but the process was. Then I was very fortunate to be able to sit at the feet of David Bohm and Roger Penrose, because they were both at Birkbeck College when I was growing up. And it was delightful to sit in the seminars with them. So Roger would be discussing his spin networks, and the spin networks were essentially process. But it wasn't until I tried to understand what Roger was doing. It was then that I went to Clifford, and I suddenly realized that Clifford was really talking about Clifford algebras. Then I went to read Clifford, and Clifford is all about process. And in fact, I had a very simple paper which I wrote in which I actually obtained the Clifford algebra by 2-point processes with no space, no time, no nothing, just the order of these processes. And that was when I was very lucky, and Ernst Binz understood what I was doing and generalized it to include the symplectic structure, because I was just doing the orthogonal structure. I think you mentioned that earlier. But this is where the symplectic structure comes in. And that's what I've been working on recently, but it's a little bit too technical to discuss at this stage.
And then you also worked with pre-space processes. Can you tell us something about that, what this pre-space is and what kind of processes there are? You're talking about moments and entities called timings, extensions, and so on. They doesn't seem to be of time or in time. What kind of these entities
well,
are?
I was cheating a little bit.
Okay.
Because the first process is to get in here, I kept time as a universal time. I wasn't interested in time as such. But seeing the movement in the Clifford aggregates, that's the vector, triangle, tetrahedron, and so on. You remember I said they transform into each other. Now that couldn't be done on a rigid basis, an ordinary classical geometrical basis. So there was a process going on. Then I got into this Kantian, Schiller, Fichte, and I saw in Fichte was saying very much the same thing, that it's not the a priori, but it's the process of how the a priori comes about. I mean, I can't remember the exact details because it's a long time ago that I read Fichte. but I'm not in my home, so I can't just put the book down and start reading it to you. But it was a real eye opener. I forget the name. I've put it's in my papers somewhere where I reference it. But it was really reading Schelling's work that really got me into thinking about this. So there again, that's the philosophy guiding me of what is.
It's interesting you mentioned Schelling. Yeah, when we're talking about the history of electromagnetism, for example, it was Schelling who had these concepts, and he put this together, electricity and magnetism. There's a great paper in the scientific journal called ISIS, I think, deals with the history of physics.
Oh, I didn't know that, Petteri. I didn't know that.
Check out the paper; it's very interesting, yes. And then the other people, other physicists, they took it up and went to the library and checked out whether Schelling could be right.
Right. No, could
In this sense, Schelling is one of the greatest philosophers of sciences because he has something to show you.
Yeah. Okay. Could you send me the reference?
Yes, I will.
Yeah. Okay.
All right.
No, I haven't seen that. I'm very interested in it.
Yeah. All right. Very good. Do we still have time? I have some questions here. What, James?
Yeah, what is, I think where the audience, I think, might want to take part.
I mean, please go ahead for maybe another, should we say maybe 15, 20 minutes tops, and then we can open up.
Oh, okay, all right. Now when we talk about processes, we could also ask something about the movement. That's the other important concept. You're talking about hollow movement and things like this. Can you elaborate?
Yeah, when I started debating with David about these ideas, we were talking about movement.
Right.
And it's wait a minute, something suddenly clicked in my brain. Yeah. No, I won't go down that path. No, I don't. This idea of movement. When I started, we were talking about movement, and I was just taking movement as movement per se. I will tell you this story. Did you know that there is two Greek words that we ought to be familiar with? Just two. Kinos. Kinos is where we get our kinematics from, and that is movement with a force. But they have another word, pheros. And pheros means just movement, a bit like the movement of a symphony orchestra, for example.
All right, now I got it.
And I was using it in that sense, but then I think it was Carl Pribram said to me, but you're moving things must move. And then I suddenly wrote, no, I'm not talking about things moving. I'm talking about this pheros.
Right.
And the interesting, I think pheronomy comes from that as a word that you won't find in the dictionary without difficulty. And it's a word that Einstein used. He's got a translated paper in The Philosophy of Vacuum by Simon Saunders and Harvey Brown. There's a translation of one of his papers there where he actually uses the word pherometry, showing this idea that he has this idea of movement without force.
Right.
And the other person who used this idea was Grassman. But otherwise, it's gone out of use for some reason or other, but it's a very useful thing for us. That was the movement that I was talking about. That was the movement that David was talking about. So then we use the idea of activity. But once again, no, we really should have hammered home that idea. I didn't know about ferrous in those days, but I've since come across it. It was a big debate in Nature in the 1890s, I think it was. Would you believe it? Where they were worried about whether it should be kinematics or ferrometry. I can't say the word, but very interesting.
And the this hollow movement, I think that's the ferrous kind of.
That's the ferrous. That's the whole ferrous. If that makes sense.
Yeah. It does make perfect sense now when you explain it, but what it is. All right.
And from that, you see, emerges the invariants, which are going to be the particles and the structures. So the invariants under this general ferrous is going to be our particles. So our particles, and we don't start with particles. This is where you asked me earlier about reductionism. We don't start with particles in this theory. We start with this ferrous, this hollow movement. And from the hollow movement, we find certain invariants. And these invariants, they're like the elementary particles. I mean, look, they were finding elementary particles which only lived for 10 to the minus 24 of a second. Is that a particle? Or is it an invariant in a movement which changes very quickly?
Yeah, some sort of very quickly. Subsistence. Somebody uses this term.
Yeah.
Subsist.
Yeah.
Okay.
And also, I mean, you know, we often think of the proton. We've got the solid nature of, you know, we're back to our reductionism. We've got our proton. We know what a proton is. But all the experiments that have been done on protons and neutrons have been such that they're mainly consisting of a sea of quarks with just 2% valence quarks. So the 2% valence quarks are telling you what it is, and all the rest is activity boiling out of it. So there is no solidity, I'm afraid. Even though, you know, we feel, but that's all the invariants that have got together and coalesced into matter.
Can you say a few words about this structure process that Bohm came about? It was in his inaugural lecture paper, I think, or the paper came out from that, if memory serves me.
Yeah, well, the idea was that, you know, we come from orbits, Bohr orbits, and the Bohr orbit makes the assumption that these are special orbits where electromagnetism doesn't hold anymore, because otherwise they'd be accelerating and they'd spiral into the nucleus.
Right.
So then the question is, what the hell does that mean? Why have you suspended it? What's the reason for? Because it gives you stable orbit. No, that's not. That's chasing your tail. So what one finds is that it's the stable structure. It then becomes a topological feature because it's the structure of the overall structure of the movement which gives rise to this topology. And that's what Einstein's first contributions to quantum mechanics was, to complete the Bohr orbit system by bringing in the Sommerfeld corrections and showing it was pure topology that did it. And there's a lovely paper in Scientific American on that. Okay, so, you know, there's more to life than just reductionism and so on. And there's more structure, and this is part of the structure, you see. The process is such that it becomes stable in that situation.
Yeah, I asked the question of reductionism also. Well, the context was a little bit different, but it came clear. But some people really are, you know, quite arrogant, and they think that, you know,
and I'm afraid
reduction all the way down, and there's nothing else there.
Yeah, no.
Yeah. Okay.
You try it experimentally, and you find a load of mess down there.
Right. Right. Well, now when we mentioned the concept of hollow movement, can you elaborate a little bit about that? What do you mean by hollow movements?
Well, that was just the general movement from which everything emerged. Mind, matter. So we have a sort of dual aspect monism there.
And hollow movement also works within the concepts of implicate order.
Yes, yeah. And essentially, it's like a vacuum state. Because remember, in quantum mechanics, you have many inequivalent vacuum states. Now, if a vacuum was nothing, how can you have inequivalent nothings?
Right.
There's only going to be one nothing.
Yeah.
So there is underlying structure, which is this hollow movement, the ground form of which matter and we emerge.
Okay. Does that have something to do with cosmology? Is there something like Bohm Hiley on cosmology, or
no? We
ideas
didn't go into cosmology.
All right.
It takes us a little bit too far.
Okay, but this David's paper that you mentioned deals with the curvature of space-time. That has
No, yeah. DeWitt, Wheeler, and Penrose were very much into quantum cosmology.
Right.
But I was interested, but not sufficiently to really go into it deeply.
Okay.
I just kept an eye on what they were doing.
Okay. So you mentioned quantum potential. We talked about a little bit about it 2 weeks ago also. Now, can you tell us something? I guess the people may know this, but what does this quantum potential do, and why some people consider it to be irrelevant?
I really don't know. I mean, the energy is there. If you look at the mathematics, it's there. If you look at Schrodinger's equation, you just take the real part under the polar decomposition of the wave function, and there it is. And in fact, when Heisenberg said it was ad hoc, I actually took the Lagrangian. This is technical stuff now. I took the Lagrangian that Heisenberg used and did the usual variational principle, Lagrange variation, get the Lagrange equations of motion. And of course, he did this to get the Schrodinger equation and its complex conjugate. You put in his Lagrangian psi equals RE to the IS. And what you find is the two equations are the two Bohm equations. So why is his not ad hoc and ours is? He gets the same, but he gets the Bohm equations and just ignore. Well, he doesn't put them down, but they're there.
Okay, so what's wrong with Bohmian mechanics? It's the same physics.
No, it's because it's mechanics.
Yeah.
It's the mechanics that is wrong. This is not a mechanism. It's an organism. And that's the key difference.
All right.
Sometimes it can be made, everything can be made to look mechanical. You know, for instance, a robot can be made to look as if it's, when it's programmed to go and plug itself into the electricity, you don't say it therefore has the idea that it wants to live, so it goes and plugs itself in. Right. That's programmed in.
Yeah.
We have the opposite. If we don't want to go and have some food, we don't. So we have that choice, and it's in that choice that it is what I call the organics.
Right. Okay. In your opinion, what are the role of scientific theories in your general worldview? For example, from your own point of view, Bohm talked about theories as maps, for example, and even as artworks. What is your?
Yeah, for me, it's just curious as to my surroundings. I want to understand the surroundings in which I live. Yeah, I'm not happy to go to the disco every Friday night and blow my mind on ecstasy or whatever it is the young do. I want to understand what's going on around me. I'm curious. I don't know why I'm still curious. You know, even after all this time.
Human nature.
Hey?
Human nature.
Yeah, it's human nature. And I'm still saying why. I'm still like a child saying, why? Why? I don't understand it. Why?
Right. How about then the role of empirical experiments? I think that Bohm was a little bit, he had some kind of a bit a negative feeling or idea about the empirical testing, especially in a sense that if science put emphasis into the empirical experiment.
No, I think he thought the experimental input is very, very important. He was a physicist in the true sense of the word. He wasn't a mathematician. Mathematicians aren't interested in one iota of what goes on in the laboratory. David Bohm was very interested in what goes on in the laboratory. And so I don't know where you got that impression from, but he was very interested. I mean, what he thought was that you couldn't, by experiments alone, determine that's the end of the story because it's correct.
Yeah.
But then he was very Popperian in that sense of saying that it's not, you don't verify a theory, you just show it's not falsifiable in that context.
Right.
Doesn't mean to say it's right.
No.
I think he was a little bit worried about that, but I maybe because of the flack that he got from the Bohm-Aronoff effect. Because the experiment was done very, very quickly after Bohm and Aronoff published their paper in Bristol. It wasn't what I would call a clean experiment, but it was quite clear that it was there. And that was published about a year or two afterwards. And I think he still got, I think it's Weisskopf said, oh, we thought it was Bohm being a maverick again or something like that.
Okay. What do you personally think of this Popperian falsification?
I think that's a good way of looking at it.
Right.
Experiment verifies that you're not wrong. It doesn't verify that you're right.
Right. Popper said something, and in matter of fact, he has a book titled Conjectures and Refutations. That's basically about conjectures and refutations. Do you agree with this? Or
yeah. Read it many years ago, Petteri. Don't ask me what's in it now. This is almost empty.
By the way, did you knew Feyerabend personally?
No, I never had the privilege of meeting him, no.
Yeah, but it seems that Bohm had a lot of discussions with Feyerabend.
A lot. They had a lot down at because Feyerabend was down at the LSE when I joined Bohm. I was a young kid at that stage, believe it or believe it not. And I'd come in from solid state physics with no idea of what quantum mechanics was, except my curiosity, which hadn't been answered in the lectures on quantum theory in the undergraduate school. Why? I'm still saying why.
Okay.
But I met Popper. Yeah, I met Popper on a number of, he was in the same seminar. I used to go to the seminars at Chelsea where Michael Redhead, Karl Popper used to go there, Jean-Pierre Vigier used to go there. And those were interesting seminars in those days. they usually be talking about the Bohm theory.
Okay. Concerning Bohm theory, do you agree with the statement that mathematical equivalence is the same thing as empirical equivalence? Because some say that.
That's a very interesting question.
All right. Good.
Which I am not going to give you an answer because I am puzzled by it myself. One of the things that triggered me off to show that the Bohm's theory fits in directly into quantum mechanics was looking at the Stone-von Neumann theorem again.
Right. Okay.
Now, and I particularly looked at the von Neumann paper, and that is an extraordinary paper. It was written just after his Mathematical Foundations of Quantum Mechanics appeared. It has absolutely nothing to do with Hilbert space. What he does, he shows that the Schrödinger representation is equivalent, no, that is unique up to a unitary transformation. Now, what a lot of physicists, I think, have done is taken it as unique and haven't realized up to a unitary transformation. And all you have to do to get the Bohm theory from the Schrödinger is to use a unitary transformation. Dirac knew that, it's in his book. So it shows you that, sorry, why are we talking about this? I've lost the point.
Well.
What was your question? Sorry.
Yeah, that whether mathematical.
Oh, yes, equivalence. Yeah. So if you have all these mathematically equivalent views of quantum mechanics, what does it tell you about the physics? That's the question I'm struggling with. I think it gives us another perspective of the physics. In other words, we need all these different, it's like a partial view. Because we're inside looking out, we need different views to see what the outside is like. We're not outside looking in where we can see the whole thing. But if we're inside looking out, we get partial views. And for me, this unitary equivalence is supplying partial views of the physics. So it's telling you something about the physics. For example, the Bohm theory is telling you something about the energy and the momentum. That's the Bohm picture. The Heisenberg picture is telling you just about the total energy. And the Bohr picture is just, the Schrödinger picture is just telling you about how things evolve in space-time, in the configuration space.
I remember that Jim Cushing's book. He was talking about this hypothetical test called relaxation times. Do you remember that?
No, but go on. What are you going to ask me?
Yeah. He just mentioned that would this experiment concerning relaxation times, if it could be conducted in a sense that the outcomes would be positive and would support Bohm's theory, would that be crucial?
Wait, wait a minute. Do you mean the Bohm theory that he published with Jeff Boob? Because
I don't know what that. I don't think that Cushing mentioned that in this.
Well, I think he may well have done. I'm sorry, you can correct me. Because I'm now talking 20, 30 years ago.
Mm-hmm. Okay.
But there was an experiment proposed about relaxation times of that particular theory, of the Bohm theory.
Mm-hmm.
And that turned out to be negative.
Okay.
The experiments showed that there wasn't this relaxation. The relaxation time was instantaneous.
Mm-hmm. Mm-hmm. Okay.
I think I do remember that.
Yeah, all right. I will check it out. Okay, I do have some questions here, but we are running out of time, and I'm sure
Yeah.
that people would like to ask some questions. But last one, quickly. What would you really would like to achieve with your physics? What would make you happy? What do you want? What do you need?
If I can complete this book, which I'm struggling to write.
Is this the popular book we're talking about now?
No, I'm talking about the definitive legacy of, oh God, doesn't it sound terrible?
All right, I got the picture, yeah. Yeah, good luck with this, and hopefully you can get going on also with this popular book, no matter how much David gives you problems.
Yeah, but very thankfully, Petteri, your face is now coming through to my bad eye, which is good news.
Okay, great. Yeah, from my behalf, Professor Hiley, thank you very much.
You're welcome. I hope I've said something of some interest.
Oh, sure. I have to check this program out at least once more. There's lots to learn. Yeah. Okay, James. Yeah.
Thank you so much, Petteri and Basil, for talking to us about, well, Basil, for your talking at the beginning about your new developments, and together talking about the philosophy of your own physics, which was really, really interesting. And yeah, so we can open up now. We've got about 15 minutes, so please feel free to ask your questions. To ask your question, you can use the raise your hand function, which is at the bottom of your screen under reactions. Or if it makes you feel more comfortable, you can always write your question in the chat and I can read it up for you. Who would like to go first? We have Niels with his hand up. Please come in.
Yes, Basil, as I've expressed before, I'm very interested in what happened when Bohm died after your last discussions about in the final chapter of the Undivided Universe, and that has spoken lots of things to me. Sorry, I'm on a Zoom meeting. I'm talking.
One of the problems with Zoom meetings.
Sorry, that was my wife. She wanted me to join her for a meal. But as I've said before, I'm in that chapter, there was also Stephen Hawking was mentioned as saying that he expected it would be computation that would actually solve all these problems at some time in the future. And having been in that business for 50 years, I can see some things that could be really useful for this discussion. But I feel that computation is being kind of pushed down, because they're saying machines can't think, machines can't do this and that. But computation per se in graph theory is nothing to do with computation. It's more to do with reason and understanding. So I realize that that there's a problem in the way we see computation. Even what was his name? The famous. I'm getting tired now, but.
I'm sorry I've had that effect on you.
No, well, I'm trying to understand everything you're saying, and it is quite draining. But I would love to do a presentation of graph theory and what we can achieve with that, because that in process theory, that is quite foundational, and we can do mighty things with that. I know, Basil, you've talked about that mathematics can't do it because we can't differentiate paths of quantum paths, and that's exactly that is what we can do with graph theory. In a sense that negative integration of the evolution of paths translates into forward unfolding differentiations, if you like. It's like a differenting broken lines. Because one of the things I've always puzzled, I do understand mathematics and differentiation and all that. I always wondered about differential equations, that it was so difficult to get anything out of that. It was too, and that I think some of our problems is different interpretations of that is really foundational to all the complication and discussions, and I think this and I think that. So I started writing up in the last.
Just because there's a few questions,
Yes,
did you?
okay. Yes, but I wanted to hear your view on computation.
Well, computation in its right place is absolutely essential.
Yes, and this is what I would like to send you some material about this.
Okay.
I started writing it up after the last Beyond Bohm, based on various opinions in the discussion group, and there's one thing that there's one algorithm that could be foundational in all of those pursuits. That's what I find interesting.
Thank you, Niels,
Yes,
and
sorry.
please your paper on Sutra to be discussed on. We'll next go to Jorge.
Yeah, thank you. Well, thank you very much for your effort in conveying deep thoughts in very limited time. I have two short questions. In your research, at some time, you had the insight of letting the distinction between operator and argument vanish. And my question is whether you have any insights on the following. In systems biology, in the study of, for instance, metabolic systems, a formalism, a mathematical formalism emerges where you, in some sense, let the distinction between operator, argument, and value vanish. So you get some sort of a tantalizing equation like F applied to F equal F as a self-referential equation. Yeah. Do you have any comments on the relationship with your own insight?
Well, that sounds like the primitive, the idempotents that I used, which are very important in the whole structure. Without the idempotents, that's P times P is equal to P, is the way I put it, rather than F times F is equal to F. So yeah, they are foundational in the whole structure.
Thank you, but this is even worse because you apply F to F. So it's not just the same as composing F with F. So you have idempotency, but I think it goes further. And for mathematician, in principle, it doesn't make any sense, but looks like you can construct a sort of solution of this by limiting processes. So well, is this not just,
I use this, as does Hermann Weyl, to get my irreducible representations in my algebras. So I'm using it as a tool, if it were, as it were.
Uh-huh. Okay. The second question was whether the ice cream cone is necessarily bounded.
Yes, there's a very interesting question. There is a fundamental law called the Bott periodicity law, which
I see.
once you get
right.
to level 8, it all starts again.
Yeah, Bott periodicity.
One level I missed out, and there's that level. Above that, there's nothing.
Uh-huh.
Well, I say there's nothing, that's not true. It's the same structure built on another structure. There's nothing new of any interest.
I see. Great. Thank you.
Okay.
Thank you, Holger, for your questions. We'll next go to Gary.
Hi, thank you so much. This was just fabulous. And I've put a number of comments into the chat about the work of a fellow by the name of Robert Rosen, who's a theoretical biologist whose work primarily focused on the distinction between mechanisms and organisms. And his feeling is that the issue relates to the presence of causal loops, and that you cannot predict how a causal loop will behave when you try to analyze it discontinuously, right? When you try to frame it, you can't, because it operates in context on a temporal continuum. And I'm wondering, my question is, can we frame this problem, right, as one that is the distinction between continuity and discontinuity, in that the implicative order is fundamentally continuous, while the explicative order is necessarily discontinuous? So that in effect, in the movement from the implicative to the explicative, time disappears. Whereas time is real and necessary and continuous in the context of the implicate order. That's my question.
Interesting question. Deep question as well. The way I look at it at the moment is this new structure that I've dug up is causing an obstruction. Because if with the old structure, before I'd realized exactly what was going on building this tower of algebras, I would say we have a universal time. And that is what is going on in the hollow movement. And then we explicate from that different views, which produces these different times. And we've got to be careful what we mean by time. We have to be more precise about the meaning of these extra parameters that are coming in. We have to identify them. And that's being a little bit difficult, but the great thing is that I've actually now identified a problem I had with Schwinger's work on the Green's functions approach to quantum mechanics. There he was introducing two times, and it wasn't clear to me why he was doing it. Now I understand why he's doing it. So it seems to be part of the building of a hierarchy that you have different times. And we have to understand what that means in detail. That's the best I can do, I'm afraid.
Thank you. That helps quite a bit. Thank you.
Thank you, Gary, for coming in. So I don't see any more questions, but we should, I guess, start closing up. Petteri, did you have any last comments, maybe even a last questions for Basil before we close? Anything to leave us with?
Well, obviously the problem in quantum mechanics is the interpretation. No, that's not right. Really?
It's also the mathematical structure. We've got the wrong, we're using the wrong mathematical structure.
I see.
I'm sorry if I sound arrogant, but it's about time I would actually put my foot down.
Oh. Well, I'm glad that I asked this question. All right. That's from me.
Okay, great. And you, Basil, any last comments you want to leave us with?
Well, no, the only comment is I wish I could find people who would actually work with me on this subject. I think they get put off by the bigwigs. Sorry if I might call them that, but I'll probably offend somebody. Who cares?
I have the impression if physicists and the younger people, especially in physics, if they would know more about philosophy and these things, they would be perhaps more interested.
Yeah, but then they go to their supervisor, and then the supervisor says, no, you won't get past, you won't get your PhD if you go down that road. That's the problem we're facing.
I understand that.
And I don't know if we can do anything about it, but I mean, when I came through, I had the privilege of being with David Bohm, and I had the privilege of being a kid of the 60s. And we had freedom, man, we had freedom. Not to squander it away, but actually to do serious investigations. Now we seem to make our youngsters go through course after course after course, who become experts. As soon as you take them off the ideas that are told to them by the course, such as this use of the Clifford algebra process and so on, they are utterly bewildered. They are utterly bewildered. And it's very sad. But there you are. That's a fact of it. This is a grumpy old man speaking, by the way. I'm just a grumpy old man.
Yes, and on that happy note, we shall close the session. No, really, thank you so much, Basil, for joining us today. It's always a great pleasure when we have you for these sessions. And Petteri, thank you so much for today's session and for last week's session. And we hope you join us again very soon.
Thank you, Petteri. Thank you. I hope I haven't given you too rough a time.
No, not at all. But I have to do some homework.
Well, thank you everything for those who joined us today and your contributions, both on chat, through your questions, or just by being there and listening to us. Before we go, I'd just like to invite you all to tomorrow's session, where we will be joined by Bill Seeger, talking about consciousness, Bohm, and the quest for intelligibility. It should be a great session, so I hope to see you then. I also wanted to invite you to a session on Wednesday, this upcoming Wednesday, of the Future Scientists, which I believe ties in with what we've talked about today a bit, where Alex Gomez-Marin will be in conversation with Professor Avi Loeb, where they'll be talking about reproducibility in science and anomalies that are rare but relevant events that can help rather than hinder scientific progress. So I hope to see you then. It should be really good. Until then, thank you again to you both and to everyone here. See you again soon here at the Bar Center. Bye-bye.
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 Bye-bye, everybody.
Bye-bye.
Thanks for listening.